Hello. Good evening, good morning, good afternoon, whenever you're viewing this. I hope you're all safe and healthy. Um, so instead of doing this lab on campus due to the current circumstances, we're going to be doing it at home. So the lab that we're going to focus on today is balanced torques. What you would have done in lab is you would have taken a meter stick and some hangers and some masses, and you would have done this experiment. We're going to do something as close as we can get on our computers. So in this lab, we'll look at rotational equilibrium conditions for a rigid bar. And locate center of gravity for a real object. So unfortunately, we won't be looking at the center of gravity, but we will be looking at something I think equally as interesting. So in the original document found in your lab manual, there is a theoretical background. I would highly recommend reading through this theoretical background. Now, this should be material that your professor covers in class. If not, I'm going to go over enough material here so that we can actually go through one example, and then it'll be your responsibility to do the other several steps that we'll need to do to complete the lab. So the theoretical background piece is a relevant piece to the lab manual. I would highly recommend reading through that. Okay. So what you will have is a modified balanced torque lab, and it's going to look something like this. I might make a few other changes, but for the most part, it'll be this. So this lab has been modified to make it able to be done at home. Any changes to the lab will be found below, and detailed description will be given in an introductory video. That's what I'm trying to do now. All right, so the equipment that you're going to need, I did not include this because I'm assuming that you all have a computer, but you'll need a computer. You will start with this introductory video. You can see that I'm making the video now, so we don't have a link for it yet, but there'll be a link here, hopefully, or it'll just be given to you. And we'll be using the website given here. Now, this is a simulation site that has some really neat physics simulations that we can do, and one of them is called Balancing Act. So the theoretical background, this has not changed. Please read this from the original lab manual, and we're going to go through one example. So the experimental procedure here is to start off by watching this introductory video, follow the instructions given. I will go step by step, like I said, with one example. So the first thing we want to do is we want to open the link above, and we want to check forces from objects, level, and rulers. And I'll show you what I mean by that right now. Okay, so here I already have the site loaded, and this is what it should look like. Okay, Balancing Act. So the first thing is you want to check your forces from objects, level, and we want to check rulers. So the rulers allows us to see how far away an object is from the pivot. This is our pivot. The level is an indicator whether or not that this is balanced in equilibrium, and this will actually give us some sort of vector representation of the forces acting on the object. Right. So the next step is we're going to go down here. We have all these different objects that we can play with. We have people, we have bricks, we have mystery objects. We're going to play with the mystery objects. So I want you to start with object A. I'm going to start with object C, just to go through an example with you. So we'll take object C, and we'll place it at the 2 meter mark. So it's placed 2 meters away from my pivot right here. The next step is I'm going to switch this on. So that's going to remove these columns. And as soon as those columns are removed, the force or the weight from this particular object creates a torque on the system, causing it to rotate. And then it eventually stops when it hits the ground. All right. So let's go back. And what we want to do is we want to balance this. So I'm going to start with just 5 kilogram bricks. That's what you're limited to. I mean, they have all different options here, so you can play on your own if you want, but I want you to just use 5 kilogram bricks. So I'm going to take the 5 kilogram brick and I'm going to start as far away as possible. And we see that has no effect on this. And I'll move that one here. And I'll just keep doing this. I'll just keep adding 5 kilogram bricks until the object responds, the system responds. In this case, we have kind of overcompensated. So I have too much torque. There's more torque on this side than there is on that side, to cause it to seat in this position. So what I'm going to do is I'm going to move this 5 kilogram brick closer to the pivot. Still too much, so let's move it even closer to the pivot. And now we see that, there we go. The system is now in equilibrium. All right, so once we have a configuration that balances the mystery box, we need to write down these distances. And I want to also draw a free body diagram. So let's look at that now. So I'm going to pull up a piece of paper so you can actually see what I'm writing down here. Okay, so this is my balanced torque lab. All right. Now, the definition for torque. Torque is equal to the force applied at some distance, d, away from a pivot, multiplied by the sine of the angle between the force and the distance vector, if you want to call it, the distance vector away from the pivot. So for example, if this is my pivot and I have a force acting on, let's say, a rigid rod somewhere out at this region, and this force is acting in this direction, F. Okay, so we know the magnitude and we know the direction in which the force is acting. This is my distance. That's my distance away from the pivot. And if I extend this line and I draw an angle here, theta, it's this angle theta between this distance and this force. Essentially what I'm doing is FD sine theta. F sine theta is going to be my force that is perpendicular to this distance here. Okay, so it's the force that's perpendicular to that distance. And if the force is already perpendicular, then the sine of 90 degrees goes to 1. And that is actually what we see for the example we're looking at. If it's not perpendicular, you have to take into account the angle between this line and your force. Okay, so that's really all I'm going to talk about here. Like I said, a lot of the details should be filled in with your professor. But what we're looking for is the sum of the torques is equal to 0. So we're looking at what's known as a static case. So this is a static case. So if we have, for example, a pivot. So here is my pivot. Here is I'll use a ruler here so I'm not so sloppy. Here is my line, the balance itself. Now I have an object out here. The mystery box, which is applying a force in this direction. Okay, so it's applying a force in that direction. And we can call this, why don't we just call this F We'll call this F2. Okay. And F2 is going to equal m2 multiplied by the acceleration of gravity. Now what we ended up doing is we put masses positioned out here on the left-hand side, and we had a mass out here, and we know the mass. We know that this is a 5 kilogram mass, so we have a 5 kilogram mass here multiplied by 9.8 meters per second squared, so that would be a force that's being applied in that direction. And we know the distance. We know that distance that it is away from the pivot. So I know that the first mass is located at a distance of, I don't want to get too sloppy here, but this is 2 meters. And we know that our mystery object is also located at 2 meters. And in the example for object C, the mystery mass is going to be much larger than my 5 kilograms. That's why it took several 5 kilogram masses to actually balance this out. So we also have another force here, right? And we have another force here. And then we had a 1, 2, 3, we had our fourth force around here. So if you're looking at that picture while I'm doing this, if you're playing along, you will actually see that each of these is 5 kilograms times 9.8. So let's actually see what that value is, 5 kilograms times 9.8. That is 49 newtons. So that means there's a force of 49 newtons here, 49 newtons here, 49 newtons here, 49 newtons here. And so those are 49 newtons. Now what's going to change is torque. If you look back here at our definition of torque, torque is equal to force times distance. In this case, the angles are all 90 degrees. So I could say in this case, the torque is just equal to force multiplied by my distances. So what that means is the further away that you are from the pivot, the larger the torque is going to be. Okay, so this is going to have a larger torque than this, and then this one will have a larger torque than that, and this one will have a smaller torque than all of those. It'll be small, and this one small, and that one small. Now, because that's closer to the pivot. So as you get closer to the pivot, the torque gets smaller. So if you ever try to open up a door at the hinge, it's extremely difficult to do. All right. So we need to record each of these distances. So the first one is at 2 meters. The second one here, this is at 1.75. I'm going to kind of write these down below here. So 1.75 meters. This one here is at 1.5 meters. This one here, 4.9, this is at 0.75. I don't know why I said 4.9. 0.75 meters. Okay, so we now know the locations of each of these. This is 2 meters, 1.75, 1.5, 0.75, and this is unknown to us. So let's talk about one other thing. So if a torque causes a rotation, there's going to be a sign associated with that. So this here, this particular torque is going to cause the seesaw to rotate in that direction. So it's going to rotate in a clockwise direction. And clockwise, make sure I get my clock right. Yeah, clockwise direction. Clockwise rotations are negative. So this would be a negative torque. So we have to keep that in mind when we're looking at these rotations. So this is going to be a negative torque. And over here, this is going to cause a rotation. If we look at this, that rotation is going to be in a counterclockwise direction. And that's going to give me a positive torque. One way I like to think about this is if you just think of the way that we label angles. If we measure an angle above the x-axis, in a counterclockwise direction, it's positive. When we measure it below the x-axis, it's in a clockwise direction, it's negative. Okay, so this is going to be negative, that's going to be positive. So let's now take a look at this equation right here. Okay, so we want to look at the sum of all of these torques. All right, so let's take the sum of the torque is equal to, when we have this first one, I'm going to start with the positives. So we have a force, all right, so we take our force, which is 49 newtons, multiplied by our distance, 2 meters. Now the angle I said between those are already 90 degrees, so the sine of 90 is 1, so I don't need to worry about that sine theta. And then we have another one. This is 1.75 meters away, but it's also 49 newtons. So 49 newtons multiplied by 1.75 meters. Great. And then we have our force located at 1.5 meters. So this will be plus 49 newtons multiplied by 1.5 meters. And we have our force that is at 0.75 meters. So plus 49 newtons multiplied by 0.75 meters. Okay, so those are all the torques that are on the left-hand side. Well, now let's look at the torque on the right-hand side. We have one, and that's that mystery box. This is going to be a negative, so minus some mystery force, but we're looking for the mass, so it's going to be minus m2 multiplied by g, so there's my force, multiplied by the distance, which is 2 meters, and this is all equal to 0. Okay, so we have just one unknown. We don't know our m2. Now the way that this is set up is kind of to your advantage, because the force is always going to be 49 newtons. Or we could even write this as 5 kilograms times 9.8 and get a nice cancellation out of G, but started this way, so we'll continue going it this way. All right, so I can rewrite this. I want to solve for m2g, so let's take my 49 newtons, and I can factor it out of these 4 terms here. So we have 49 newtons multiplied by 2 plus 1.75, so we have 2 meters, plus 1.75 meters, plus 1.5 meters, plus 0.75 meters. And then this, I'm going to throw this on the other side of my equal sign. So I'm solving for m anyways. I'm solving for m, yeah, m2 anyways. So this is equal to, we have m2 multiplied by g multiplied by 2 meters. Right. So let's sum all of this up, and then we'll multiply by 49. So we have 2 times 1.75 multiplied by 1.5, plus 1.5, plus 0.75. Okay, great. So that's 6, right? Just double checking. Awesome. So that's 6. So we have 49 newtons multiplied by 6 meters is equal to m2 times, now g is 9.8, so I'll put that here, 9.8 meters per second squared multiplied by 2 meters. So 49 times 6, that's 294 meters times newtons. And this is equal, that's just the units that we use for torque. And this is equal to m2. And I want to divide through by this 9.8 times 2. So let's divide through by 9.8 meters per second squared times 2 meters. Now let's see what this comes out to be. We see that, this meter cancels with this, and then we have an acceleration under a force, which is going to leave me with a kilogram. Right, so we have 294 divided by 9.8 multiplied by 2. Oh, so M2 is equal to 15 kilograms. Perfect. Okay. So, and of course, I went below the I went below that. There we go. Okay. Let me scroll this up a little bit now. I explained it and I didn't move the paper up. Great. So we have, I'll get better with these videos. We have 49 newtons times 6 is equal to all of this. We did all of that out. I explained it, and then here's the actual math. Sorry about that. So that's 15 kilograms. Okay. So this is the approach I would like for you to take to solve, let's see here, to solve all of our mystery boxes. So do it for mystery box A, box B. I did it for C with you. Box D, E, F, G, H. Now I do have to mention one thing. You may find a box that is too heavy. And you can fill this whole thing up with 5 kilogram masses and it doesn't budge. If that is the case, start moving that particular box inward, closer to the pivot, so the amount of torque that it is applying is less. And then rearrange your configuration that way. So you can do that for masses that are very heavy. Okay, so if this is 15 kilograms, I'm just playing, right? So if this has a mass of 15 kilograms, some of them have some strange masses that are not 15 kilograms, even integers of 5, but this particular one is. This should balance it out. Let's see if it actually does. Yes, perfect. Okay, so we calculated the mass using only 5 kilogram masses, and I did that because you could easily have put this down and checked it, but I wanted you to figure out that you can use multiple masses at different locations that supply different torques that will, in the end, give the same result as a single 15 kilogram mass located at 2 meters. So let me pull this up again. So I went through the steps already with you. So you're going to start with object A. We did object C, place it at 2 meters to the right of the pivot, then move the slider to the right directly beneath the pivot. This way move the pillars and you will see the balance tip to the right. Now switch the objects back to the bricks and choose only 5 kilogram mass bricks. Place as many as needed in whatever configuration that will balance the scale or put the system back into equilibrium. When the system is in equilibrium, the leveling arrows will turn green. Record the location of each 5 kilogram brick and the location of the mystery object from the pivot. Note, and I just talked about this, if the mystery object is too heavy and does not balance when every location is filled with the 5 kilogram bricks, you can move the position of the mystery object closer to the pivot until you can find a configuration that balances. Once all locations are determined, draw a free body diagram and use the sum of torques to determine the mass of the mystery object. Repeat steps 2 through 7 for all remaining mystery blocks. So including the example I did with you here, there should be a total of 8 blocks. Now the last section of your lab is usually data analysis and uncertainty estimates. So I am replacing that with some of these questions. So the data analysis uncertainty is not going to be necessary for this lab. What you will actually look at is these questions instead, which I think are more relevant and kind of do a little bit of an expansion on what we did. So this section is replaced with the following questions. What are the 8 mystery masses? Okay, so that's just copy and paste down. What are the uncertainties when using simulations? So this is a curious question. I'm a computational physicist, so I do a lot of simulations. So the question is, are there uncertainties when you do simulations, and at what limitations can we ignore those uncertainties if there are? So, think about it, explain. I do a little Google searching to figure this out. If we had 2 unknown masses on opposite sides of the pivot, could we calculate both masses given just the information used in the experiment that we did? Explain. Okay, and then this kind of piggybacks off of this question. Given the diagram below, it's on the next page, calculate the unknown masses. The mass of the balance, m sub m, is equal to 1 kilogram, and the normal force is 330 newtons. And here is my image. So we have our normal force, which is pointing up here, the force from the weight of the balance. Our object 2, F2, is at 1.5 meters, and F1 I put at 1 meter. So you need to figure out what M1 and M2 is. Okay. So I hope that this was helpful. I hope you get something out of this. I know it's not the same as doing it hands-on, but with this particular simulation, you can play around with it a little bit and hopefully have some fun with it and learn something at the same time. All right. So that is it.